Okay, so for this example, we have the water discharge from an orifice under a head of 1.2 meter. From the surface of the tank to the orifice is 1.2 meter. And then to determine the coefficient of CV, if the jet flow vertically to a distance of y, okay, so it flows vertically, distance of y 0.5 meter, and a horizontal distance of x 1.5 meter from the vena contracta. So by rewriting the x equal to Vt and y is half of the Gt, so V may have x over t, and t is equal to 2y over g square root. And then substituting to velocity jet, we have the V actual equal to the gi square over 2y. So just put all the values into this equation, and we get the velocity actual is 4.7 meter per second. So therefore, to calculate the velocity theory, we have the power of 2 GH, and then we get 4.852 meter per second. So therefore, by using the formula for coefficient of velocity, we have 4.7, that is velocity actual over the velocity theory, so we get 0.968. So let's look into this third example. So a vertical circular tank of diameter 1.25 meter is fitted with a sharp edge orifice at its base. So the diameter has a diameter of 50 when the flow of water into the tank was stopped. The time taken to lower the head from 2 to 7.5 meter was 240 seconds. So estimate the flow rate through the orifice under the steady head of 2 meter. So now we have the area of the tank is pi j square. That is j is the diameter 1.25 divided by 2, so you have 0.625 square. Okay, so we have the area of tank is 1.227 meter square. And then to calculate the area of orifice, that is pi j square, so we have 1.963 exponent negative 3 meter square. So time taken, okay, so estimate the time taken to lower the head from 2 meter to 0.75 meter. Okay, so time is 240 seconds. So we have 2 times area of the tank times with the head of 2, okay, power of 0.5 minus head lower head, that is 0.75, okay, over the CD, okay, times with the area of orifice, and then times with the 2G. Okay, so we have the coefficient of discharge of 0.645. So we calculate the velocity theory by using the formula of square root of 2GH, and then you get 6.264 meter per second. And then you use to calculate the theoretical flow rate. So we have A times V, so we have A of the tank, that is 1.963 times with the velocity theory, that is 6.264. So we get 0.0123 meter cube per second. So the flow rate in the real is equal to the coefficient times the flow rate of the theory. So we have 0.645 times with the flow rate theory, 0.012. So you get 7.931 times exponent negative 3 meter cube per second. So now let's look into the large orifice. So if the vertical height of an orifice is larger, then the head producing flow is substantially less at the top of the opening than the bottom. So formula used for small orifice are no longer applicable. Okay, so we use the method of the integration from top to bottom of the opening to get the Q theory, hence the Q actual, if the CD is known. Okay, so by considering a water living through the strip, so we have this strip. Okay, so by using the velocity equal to square root of 2gh, we can integrate the flow rate by the velocity times the differential of area equal to the velocity times the b by times b times with the differential in height. So by integrating this value, so we have the Q theory by 2/3 times b times the 2g h power of 1.5 minus h power of 1.5. Okay, so let's look into this example. The water flows from a storage tank through a rectangular orifice. So we have this rectangular orifice opening, okay, large orifice with a 2 meter height and 1.2 meter wide. Okay, 1.2 wide and 2 high. Calculate the discharge when the free surface in the tank is 0.5 above the opening. Okay, so the height from the orifice to the water surface is 0.5. So assume the coefficient of discharge is 0.64. So you just use formula for Q actual equal to CD times 2/3 times B. Okay, the B of the orifice times with the 2G. Okay, so height is 2.5. Okay, H2 2.5 minus H1 0.5. Okay, so this one is 0.5. Yeah, so by solving this, you get 8.16 meter cube per second. Okay, now let's look into sharp crested weir or notch. So a notch is an opening in the side of a measuring tank or reservoir extending above the free surface. So basically, a weir is a notch in a large scale. So we have, for example, this is the side view. Okay, so we have the opening. Okay, so this is the wall of the weir. So we have this opening. Okay, so this discharge may flow out from this opening to the atmosphere. Okay, so this is called the notch, or in a large scale we can consider a weir is a notch. Okay, so same method applied for a large orifice. So here we have the side view of the we can say river. So this is the difference of the width, okay, with the difference of the height of the water level inside the river. Okay, so area of strip equal to the area of strip is equal to the width times the difference of the height, and then the velocity through the strip is the square root of 2gh. So the discharge can be calculated by using Q equal to AV. However, A can be calculated by using B times with the difference of the height times with the velocity is the integration is the square root of 2gh. So now we can calculate the Q theory by using 2gh integrate to the 0 to h level times with the bh power of 1/2dh. So we have two types of the weir. First, rectangular notch, and second, V notch. So rectangular, basically we have the B, the base B, okay, and then we have the height H. So B is constant. Okay, so B is constant, and and then we can calculate the Q equal to B times square root of 2G, and then this is the integration of H. Alright, so we can use this formula to calculate the flow rate for the rectangular notch. However, for the V notch, we have B equal to 2H, the height, okay, minus the difference in the height, okay, tangent theta over 2, because we have the angle here. And then we can calculate the Q equal to 8 over 15 2G times tan theta over 2 H power of 5 over 2. Alright, so we will look into this example in the next video.